All right, it's Mr. Bergman here. I'm going to be doing a few problems on video and submitting them onto my YouTube channel for you to just get some help and some practice on physics. So I'm probably going to upload them as 3 separate videos. Here's my first one. I'm choosing a couple homework problems that I think are challenging and yet what I think you should be able to perform in order to be ready for our physics quizzes, our physics test. So I'm going to be doing number 37 first. This is on the second part of the homework. The question says a force of 35 newtons is required to start a 6 kilogram box moving across a horizontal concrete floor. And this is a 2-part question. The first part is, what is the coefficient of friction between the box and the floor? And then later on down here it says if the 35 Newton force continues, the box accelerates at 0.6 meters per second squared. What is the coefficient of kinetic friction? So the basic idea here is that this question is testing your ideas, your knowledge on static friction, which I'm just going to write in here. How to solve problems using static friction and how to solve problems using kinetic friction, which we'll do later. Now, one thing I want to kind of go over, review on, which you hopefully have started to learn about, is what's called a free body diagram. For these forces or dynamics problems, free body diagrams are really essential. And what they do is they set up forces. We can use Newton's laws to try to predict what other forces are and essentially how we're going to solve a problem using equations derived from the free body diagram. So let's set up a free body diagram so we can better understand this first part here. Okay, so before we even do that, let's just understand this problem. We are moving a box. So here's a little glass pumpkin we'll use as a box. And the idea here is that we are applying a force on it, and we are moving it across a horizontal concrete floor. Now, from your friction lab, you should have learned that when you pull an object, ideally, there's 2 types of frictions. There's a friction associated with the object at rest, and there's an amount of friction associated when the object is moving. So imagine the situation. I'm pulling this pumpkin. It's at rest. I start pulling the pumpkin. So I'm applying a force, I'm increasing that force, and as long as it's under some minimum value, the pumpkin doesn't move, it stays at rest. And so this is what we call the maximum static friction force. And static friction can be anything below that amount, so it doesn't have to be this, the static frictional force, but it can be this at the most and anything under it. So I'm steadily increasing this force, I'm increasing it. Eventually I hit that, and then I can start pulling my pumpkin at constant velocity. When I'm pulling the pumpkin at constant velocity, the amount of force needed to move it is actually less to move it at a constant rate. And so we call this kinetic friction, or the friction associated with movement. It doesn't take as much friction force, there's not as much frictional force when an object is sliding or moving versus when it's at rest. And you hopefully have went into some details about why that's the case. The basic explanation is that at the atomic level or the microscopic level, the 2 objects have they're rough. They have ridges, and when they're at rest, they're you can imagine sort of like a jigsaw puzzle. They're all connected together. It takes a little bit more force to break that contact. Once you do, however, you can imagine them sliding across each other, sort of like this. There's less force needed for them to slide back and forth as long as they continue sliding back and forth. Okay? So the idea here is that we are, in this first problem, what is the coefficient of friction between the box and the floor? It says this is the minimum force, essentially, to get the box to start moving. So we are basically given I said minimum, but basically what the maximum amount of static friction is that's possible here. And we're going to utilize that to actually solve this problem. But before we do that, we need to set up a free body diagram. So I'm going to draw a very basic picture here representing my box and the floor. And on top of that, I'm going to overlay a free body diagram of the situation. The first force that we're going to apply here, and just a very basic summary, free body diagram is a diagram of all the forces on an object. You draw these as vectors, as arrows. Now, one interesting thing here to note is that it says the amount of force required to start moving a box across a horizontal floor. So here we can assume that really the net force is going to be 0 here. To start moving basically means we don't have any additional force to accelerate it, just enough to get it to start moving at a constant velocity, we'll say. So what are some forces we can draw? Well, the easiest one that you should pretty much always draw, unless you're like way out in outer space, which we're not, is going to be the force of gravity. Force of gravity acting down on the block, right? The second one, which will often be drawn, especially if the object's on the floor, is what's called the normal force. And this is the force from the floor to the block that is keeping the block from, say, not accelerating through the floor, right? It's the natural force that something sitting on the ground gets from the ground. Now, we are trying to push this or pull this block, we'll say to the right. And so we're going to describe this as the pushing or pulling force. And then there is going to finally be a force of friction here. And as we said, that in this case, we're finding the minimum amount of force necessary to get it to start moving. So we can say forces are basically balanced here. The net force is 0. Anything more, and the block does start to move. And so this last component here is the force of friction, which is resisting the object from being pushed or pulled to the right. So what can we say? We can say the net forces are all 0. But we are trying to actually figure something out in this problem. And we are trying to figure out something about friction, right? So we want to focus in not on the y-axis, but on the x-axis. What we can write here, because we know that the net force is 0, we can say that it's 0 because the pulling force is equal to the force of friction. So if I take the pulling force and minus the force of friction, that is a true statement. This causes the expression to be 0. Now I can take this statement, rewrite it, move the force of friction to the other side, and I can say that force of friction is equal to the force of the pulling. Now once I've said that, I can add some more information here. I know that the force of pulling is 35 newtons, so that I know. The force of friction, I could say is 35 newtons, but I don't really want to know that. I want to know what the coefficient is. So I'm going to pull this apart a little more. What is the force of friction? It's an equation, and you should know this. It will be given to you on problems, on tests, but it's useful to always remember that it's equal to a coefficient times the normal force. The idea here is if there's more force from the ground, going back to this picture here, if you know, the force of gravity causes an object to go into the ground, right? So more compression into the ground means that we'll have more force or resistance, more force will be necessary to move the object. So at this point, the only force that's causing normal force is the force of gravity. That's what's pushing the object into the ground. And so essentially, in this case, the normal force is equal to the force of gravity. So let me just make sure this is clear in all my equations here. This is the equation I'm going to substitute for the frictional force. But on top of that, from our free body diagram, and this is why they're so useful, we can see that the normal force is equal to the force of gravity. And another equation you should obviously know is that the force of gravity on an object is mass times gravity. Right? So we're going to plug this substitution in here as well. All right, so this is going to give us mu coefficient times the normal force, which will be coefficient times mass times gravity. And because we're finding static, let's just note that with a little s right here. So let's do all our substitutions. So we're going to plug in, and I'm going to do this, I'm going to show all my work. So we're going to start by substituting the force of friction for mu s times the normal force is equal to the force of pushing or pulling. And then we're going to do this again. So I'm just going to draw a little arrow. We're going to substitute the normal force for mass times gravity times the force of the push. Okay, so before we do anything else, let's just make sure we know what we're finding. We're finding the coefficient of static friction, right? And fortunately, we actually have this in our new expression. We just need to move the equations, or sorry, the variables around to actually solve for it. So this is a pretty simple problem when it comes down to it. I just need to move my mass and gravity over to the other side. So to do that, and they're being multiplied, I need to divide both of them. And so I get the force of pushing or pulling divided by mass times gravity is equal to the static coefficient of friction. Now they give us everything that we need. The pushing or pulling force, as said already, is 35 newtons. The mass is 6 kilograms. And gravity is 9.8, assumingly it's on Earth. So let's go ahead and crunch our numbers now. (35 over 6 times 9.8). We get 0.595. And this is a little tricky to see, but the units actually cancel here. Newtons is a derived unit. It has a bunch of meters and seconds and stuff in it, kilograms too. So just bear with me here. Understand that the units actually cancel when you get a coefficient. Coefficients have usually no units. That's one thing to keep in mind. So there is our answer for the first part of this, 0.595. Just double checking that is the case. Yep, it rounds up to about 0.6 in my answer key. All right, now the next part of this problem says if the 35 Newton force continues, the box accelerates at 0.60 meters per second squared. What is the coefficient of kinetic friction here? So now we're being asked about kinetic friction, and this is where things are a little different. As soon as our block starts moving, as we said, there is less friction required to keep it moving at constant speed. But remember what we said is that we applied the maximum static frictional force to get it to start moving. So we are essentially continuing to apply that additional force, even though a smaller amount of force should be necessary to keep it moving at constant speed. That means that this difference here, because we're continuing to apply this, that's going to result in a net force that's going to accelerate our block and make it go faster. So to understand that a little better, let's draw a free body diagram here. First, it literally tells us in the problem that it's accelerating. So one thing you can do to help yourself is just realize there must be a net force. In a free body diagram, a net force that's not zero basically means that there's a summation where there's an arrow longer than another arrow. So here all of the arrows are equally long, they cancel. But in our new free body diagram for this situation, because there's a net acceleration, there should be an arrow longer than something else that causes it to not cancel out completely, right? So here's my net force free body diagram. What is causing that? Let's draw that. So again, we have gravity. Nothing's really changed about that. Here's my force of gravity. And the next thing is my normal force. Nothing's really changed about that either. The block is the same block. And then now I have this, I still have this pushing force. Let me draw that. I kind of drew that as light blue, didn't I? Let me redo that. And now the thing that causes the net force to be not zero is because the force of friction is no longer the same value as the pulling force. So I'm going to draw this force of friction now shorter. It's still 35 newtons. Or no, sorry, I'm sorry, the pulling force is 35 newtons. The frictional force must not be 35 newtons, which is resulting in a net force. And you might be noticing here my vector is too long. When I cancel these two out, my vector is going to actually look more like this. So I do apologize, just ignore it. But here's my net force. Okay, so we are going to solve for the coefficient of kinetic friction by utilizing our free body diagram. Just like before, we are going to set this equation up. And the easiest way to find the coefficient of kinetic friction is looking in the x-axis again. That's where you're going to find an equation that will contain the coefficient of friction because it's in the x-axis, or it applies itself in the x-axis. So the net force is no longer 0 in the x-axis. It's actually equal to the mass of the object times the net acceleration. This is important to always remember that. The net force, when it's not 0, it's always equal to mass times the net acceleration. This is really a fundamental thing. You might want to just put this down in your notes. You can always apply this to a problem and turn an F net into M times A. It's one thing that throws people off, is forgetting you can do that. Okay, so so MA, the net acceleration, is equal to what? We said it's not equal to 0, so what is it equal to? It's equal to the force of the pushing or pulling minus the force of friction. Nothing's really changed. It's the same thing as up here. It's no longer equal to 0. So we can't say the force of friction is equal to the force of pulling. In fact, what we can say is the force of pulling is greater than the force of friction. Not that we really want to say that at this moment, but you just want to keep that in mind. So we want to solve the coefficient of friction, right? So we're going to do just like we did before. We're going to do some substitutions. We are going to substitute, and I'm going to show as much work this time. We already know that the force of gravity is responsible for the normal force. So I'm going to substitute this equation for the force of friction, and hopefully by looking up here you understand where I was able to get that. Of course, now we're using kinetic, so I put a little k there instead. So here's my substitution. Let's go ahead and rewrite it now. Mass times the net acceleration is equal to the force of the pushing or pulling, which we have, it's 35, and mu of k times mass times gravity. Okay, and as we know, we want to find mu of k, the coefficient of kinetic friction, and we know a bunch of stuff about this, right? We know the box is 6 kilograms, so we can plug that in there. We know that the force of the pulling is 35, and we know gravity is 9.8. So we literally, and we know the acceleration is 0.6. So we have everything. We just need to rearrange the algebra and solve. So how can we do this? Well, we can move this to the other side, makes it positive, and we can move this to the other side, makes it negative. So moving this over here, because this is two additive or subtractive terms, we have to positive. We have to add it to the other side. That gives us positive mu of k times mass times gravity is equal to the force of pulling, and then we can move this guy to the other side. And we would do that by subtracting it since there's multiple terms. So this is just moving things around, making our mu a positive value so it's not negative. We don't have to worry about multiplying by -1 or whatever. Now we divide both sides by, since there's only one term here, to get rid of the mass times gravity, we divide both sides by mass times gravity. Cancels out. And we get mu of k is equal to the force of pulling minus the mass times the net acceleration divided by mass times gravity. Note that we can't actually cancel mass out because this term here, the force of pulling, doesn't have mass. So let's go ahead and plug everything in. This is 35, this is 6, and normally you would write units in here, but I'm just going to go through this quickly, so I'm not going to bother. And let's go ahead and solve. One thing to check your answers, to check your understanding here, well, check your answer, is typically forces of kinetic, coefficients of kinetic friction should be less than static, right? Because it takes less force to drag it at constant speed. So our answer should be less, hopefully, than 0.595. If it's not, then we probably hit a problem. And sure enough, it is less. It's not hugely less, but it is less by a certain amount, 0.53. Okay, So this is a very useful problem. It reviews free body diagrams. It's a little bit challenging of a problem, so I think it's a little over kind of what expectation I have for you for the quiz that you'll be taking on Friday or Tuesday, depending on how it gets done. But I think it's a very useful problem, kind of showing, highlighting free body diagrams, how to draw net forces in one dimension, and utilize a little bit from a second dimension to figure out a problem. All right.